Hello, everyone. On behalf of my colleagues, welcome to this month's talk from the Johns Hopkins Institute for Assured Autonomy seminar series, co-sponsored by the Computer Science Department of the Whiting School of Engineering. Each month, we will have a talk on research topics at the intersection of assurance and autonomy. This seminar will be recorded. Today's speaker is Laura Freeman. Dr. Laura Freeman is a research associate professor of statistics and the director of Intelligence Systems Lab at the Virginia Tech Hume Center. Her research leverages experimental methods and research that brings together cyber physical systems, data science, AI, and machine learning to address critical challenges in national security. She is a Hub faculty member at the Commonwealth Cyber Initiative and leads research in AI assurance. She develops new methods for test and evaluation, focusing on emerging system technology. She's also the Assistant Dean for Research. In that capacity, she works to shape research directions and collaborations across the College of Science in the National Capital Region. Previously, Dr. Freeman was the Assistant Director of the Operational Evaluation Division at the Institute for Defense Analyses. Dr. Freeman has a BS in Aerospace Engineering, an MS in Statistics, and a PhD in Statistics, all from Virginia Tech. Today, Dr. Freeman will talk about test methods for assuring artificial intelligence. Welcome, Laura. Over to you.
Sorry, I practiced that beforehand and then forgot to unmute myself and got in an OODA loop there. Thanks, David, for the excellent introduction. Hopefully you all are seeing my slides at this point. All right, so I'm excited to be here today talking to you all about test methods for assuring artificial intelligence. I'm going to be kind of pitching to you today test and evaluation as a process for achieving artificial intelligence assurance. And the flow of the talk is really, I'm going to talk about kind of when I think about assurance, how am I defining it, why test and evaluation processes, and I'll define what I mean by those, are the systematic processes that we need to assure systems that leverage artificial intelligence. And then I'm going to deep dive into one of the methods that we're really focusing on, defining operational envelopes, kind of leveraging, you know, when you think about a fighter jet or an aircraft, they have an operating envelope, they have a flight envelope. We're using kind of similar constructs to think about how do we define the envelope for our AI algorithms and our AI algorithms embedded in systems. So that's the plan. We'll do kind of high level and then drill down to a very more technical, specific way of thinking about operating envelopes. So to kick us off, I want to talk about kind of what I think about when we define AI assurance, and our research team, I think, is probably about ready to kill me on this one, because every time we write down the definition or kind of think about what it is, it changes. But a few points that I want to highlight kind of going forward is that when we think about AI adoption, I'm not thinking about AI adoption and helping me think about what Netflix movie should I watch next. It's more if something like the F-35 is going to start implementing AI algorithms in doing detection of threats. How do we know that we can trust that in this mission critical role? And so this wide scale of adoption of AI is going to require that we can assure it. So when I'm leveraging the definition of software assurance and quality assurance when thinking about that. And so a high level to think about AI assurance is the level of confidence that a system leveraging these AI algorithms or functions will operate as intended, free from vulnerabilities throughout the life cycle of the system. And I have the word system bolded there because it's not just about the algorithm, but what you see right now in the research, and even what I'll show you some of today, is focused on the algorithm. But we need to put that in a systems context because it's not the algorithm that's going to be out there in the field. It's going to be an aircraft with that algorithm collecting data in real time. And that's really the capability that we need assured. I'll focus on systematic activities. I don't think there's any one size fits all solution for AI assurance. It needs to be more of a systematic activity and a framework for providing the necessary information to do all these things like saying the outcomes are valid, verified, data-driven, trustworthy, explainable, ethical in the context of its deployment, and unbiased and fair. And so this little figure on the right-hand side, this was actually something our Commonwealth Cyber Initiative AI Assurance Group put together when thinking about what are all these different dimensions of assurance. And I'll hit on each of these in terms of our methods as we go through today. So why is it that we need a framework for AI assurance? And it's not just, oh, here's a great method. Well, as you all, I'm sure, are well aware, there's lots of different data types out there: images, videos, geospatial, there's network traffic, there's time series data. It can be labeled and unlabeled. There's different goals that we might have for our algorithms. And of course, there's lots of different types of algorithms. Each one of those dimensions will impact, what makes a successful outcome. And then more than that, what makes a good algorithm depends on what is the mission, what is the problem we're trying to address, the type and available data, the complexity of the system and how it is integrated with the system to include the humans operating it. So all these levels of complexity lead to, well, there's not going to be any one size fits all solution, but rather we need a process to go through to show that we have enough information to assure that algorithm. Another layer that I kind of layer into my context, I was actually talking to one of our machine learning researchers about some of the work we were doing the other day. And I was like, well, we don't have any idea what the algorithm is. The vendor delivers it, and we have to figure out whether we're willing to accept it. And this is, common in the DoD. There's lots of discussion going on right now in acquisition reform. And should we be buying more technical data rights? What technical data do we need? But for the most part, the government right now is not buying that secret sauce. I'll come back to that in an example in a little bit. And so we need the ability, or the government needs the ability, which motivates a lot of my research, to assure these algorithms in the absence of that information about, well, is this a deep neural network or is it a support vector machine? And so a framework process is going to help us address that. So as David mentioned, before I came to Virginia Tech, I was actually working at the Institute for Defense Analyses, supporting test and evaluation in the DoD. And operational tests and evaluation specifically. And for those of you who are not familiar with the DoD test and evaluation process, it's the organizations that conduct T&E in the DoD are doing so to do exactly that, to support decisions that come down the pipeline. So should we go to a low rate production? Should we go to full rate production? Should we field this system? And they have an existing framework for thinking about, well, how do I actually generate that information? And so I'll holistically describe it here as, first of all, we need to understand what the mission of that system or the users accomplishing that mission that are going to use this system is. What are the different systems? What are the different functions that it has to accomplish? And then from that, we need to understand what questions need to be answered in our test and evaluation process. From there, we can derive the evaluation strategy, performance measures, metrics, what is an acceptable level of performance, and then the factors or those independent variables, if you will, that are going to affect the performance measures and therefore the evaluation. We then design test scenarios by using often a field of statistics called design of experiments. We then actually go out and conduct those experiments, analyze the data, and provide feedback into future test planning. And so that's what I'd say kind of exists today, a very systematic process for thinking about what data you need to answer the questions at hand. But I'll put a shameless plug in for an article that I put together back in January of 2020. So it wasn't informed by a lot of this research yet because I joined Virginia Tech in 2019. But you can see here, thinking about test and evaluation and how it needs to evolve for AI. Is the theme of this article. And this little picture, you don't need to see it to really understand it, but this comes from a Defense Science Board report on software and defense systems. And it's all the legacy aircraft coming up to the F-35. And this big block here at the end is the F-35 Block 3F, how many lines of software code. So there's been this exponential growth in code that the government is not paying for access to. We have no idea what's going on in some of these lines of code. But what we can do is use the F-35 in the context that we're going to use it in the field, collect data, and therefore understand the risks that we have. Now, while we do have these existing T&E processes, I highlight here several different themes on how they need to update to be ready for AI. Today, I'm going to deep dive on only a subset of these, and that's really this theme 5, AI systems require a risk-based test approach, and that has to be based on how you're going to use the system. But there's lots of, I think each one of these themes, well, maybe not workforce development, but each one of these themes is kind of a research area in itself. So theme 7, an expanded definition of threat, is necessary when you think about AI. There's all sorts of research going on in adversarial AI, adversarial learning. And so all of these things kind of come into the processes that we need. And I'm just going to pick my favorite one of the day to talk to you about. I'll also hit on a little bit on whether testing and evaluation is a continuum and how we take that information going forward. So right now, each test phase, I'll actually pop over to this picture, which should look somewhat familiar for those of you who have seen the systems engineering V before. But right now, a lot of what our test and evaluation process looks like is focused on the right-hand side of the V going up. So we have unit testing and integration, then we integrate into the system, and we have systems integration testing. Then we get the full system, and the last phase of testing that the DoD does right now is really operational testing, which sits right here at the top of full system testing before deployment, where we put the system in the field with the operational users on as realistic range as we possibly can, and we collect data to support that fielding decision. That is not going to cut it for AI, and arguably it didn't cut it already for software, because a lot of our capability now can be upgraded through software or through the algorithms itself. And so this picture, our friends at AFOTech, the Air Force Operational Tests and Evaluation Center, built this for us based on some joint research with Purdue. But basically we were looking at, well, when do I need more information in my test and evaluation framework? And there could be things like the mission objective change, which I'll deep dive on today. There could be a degradation in your payload. If you could undergo an adversarial attack, and each time that happens, you're going to want to re-baseline. But additionally, you need the ability to be collecting data as you're fielded and kind of understand how things change over time. And so we were just providing examples of how you might use things like Bayesian hierarchical models to combine information, or optimal learning to pick the next points. Maybe if you have a payload degradation, you have to re-baseline, and some techniques you could use there. And so all of these things in kind of the big picture of AI assurance come into play, and test and evaluation provides that framework and process. I think we need to say, here's the problem I'm trying to solve, how much data do I need? And not just how much data do I need, but where do I need that data? So a few research challenges in AI assurance that we're diving into right now are listed here. And so I'll skip problem 1 because I'm going to come back to that in depth. But problem 2, we need to understand kind of model robustness for available data. And then problem 3, also related, optimizing. I put optimizing in quotes because we might just want to understand the robustness of the complex configurations and machine learning models. And those places we're looking at things like space filling designs to do hyperparameter robustness, and then optimizing our algorithms across different configurations. There are a million different choices that you have when you're tuning algorithms. And so how do we, kind of know what the best choices are for the situation at hand? We're also doing work in developing metrics for AI assurance, coming back to things like fairness and bias and explainability, to include AI integration with human teams. And then finally, an area of emphasis is characterizing AI capabilities in complex systems, again, including those humans. So what I'm going to focus on today in kind of a deep dive is defining operating envelopes for artificial intelligence in support of this AI assurance quest. And we'll connect into all sorts of themes on assurance as we go. So first, let's get a motivating problem. So here, the Plains data set is a data set that's available. It was on Kaggle, I think, but there's also like challenge.gov data sets. I think it was on there. But anyway, this data set includes plains, and you can see an example of the plain here in Southern California with different backgrounds and contrasts. In Southern California, And we've got a little picture here to, foreshadow where we might be going with this. But the question is, well, what if my mission shifts to Northern California? And these types of things happen all the time. In the DoD context, we shifted from Iraq to Afghanistan. What if we want to go to the Arctic next month and we're training all of our algorithms in Afghanistan? Like, how do those deploy? So this is a very operationally relevant question. And some of the things we might ask ourselves is, how can we ensure that a model continues to perform as expected as it's deployed? So say you stay in Southern California, but there's been a lot of fires and droughts, and actually those have most been in the north. But with some of the shifts in rainfall, how do we know that our algorithm is still going to be working? Can we detect a drop in performance and react to it? When we move to Northern California, can we anticipate that drop in performance, and what can we do about it? And can we provide reliable guarantees on that expected performance? And of course, labeling data is expensive, training models is expensive. So how can we do this all efficiently? So our approach, this is collaborative research, Virginia Tech, UVA, and Old Dominion University. And so we have taken kind of a bimodal approach to thinking about what is the operating envelope of my AI algorithm. And I'm going to hit two different aspects to that. What we're calling transfer distance, because we were first kind of motivated by a transfer learning problem, but also let's say, kind of transfer distance, we're thinking holistically is kind of any distance between two types of data is how we're thinking about it. And then combinatorial coverage, which looks at, can I use, we're going to call it metadata, but we've kind of expanded our thinking to be machine learning features in general, to understand how much coverage do I have across that. And we think this will be useful not only in a transfer learning context, but say the government develops a bunch of models, a model zoo, if you will, with different data training sets for different models, or different modeling techniques trained on the same data set. Can I use these metrics to pick the best available for the problem at hand? Or if I have lots of models and they're trained in different situations or different data sets, can I ensemble models from this model zoo to get the optimal performance? If I do see that a difference is coming, can I do something that's a little bit more cost effective by selecting targeted data? And if I need to go get more data, can I identify unlabeled data that's going to be the most beneficial to label next, so we can prioritize that in our machine learning pipelines? And then finally, identify labeled data to collect based on metrics. So here's the setup in the plains data. So we have data in the south, in the north, and you can see here we're just training over multiple iterations. And if you use the south and the north to train and then predict test collectively, there's no transfer learning problem. But if we only train on south and then predict on the south, or train on south and predict in the north, we see this delta in performance. And so this is our transfer learning problem directly. So can we anticipate that detected the drop in performance? And if we can, what can we do about it? So here we have all the data, but if you were to say, put your head in the space where, okay, now I'm in the south and I'm going to move to the north. So I don't have this data to know that that gap is there. Can we predict that that's going to happen? Is kind of the first question. And if so, what can we do about it? So we're going to use this twofold approach of transfer distance and combinatorial coverage to define our operating envelope. And then I'll show some results where we use transfer learning to kind of answer all those questions to bring it home. But I'll add that as the system, right now we're just talking about south to north because we're using a completely open data set that has all the fun limitations of an open data set. But we're also interested in what if the system evolves over time? Can we be monitoring these metrics and using them to define our envelope so that we have some alert of where we might fail to generalize as time goes on? And just to really drive kind of the mission scenario home, there's also the concept of kind of before you deploy. So you have data sources that you think are as representative of the environment, the target environment that you can, you're training, you want to be able to quantify, where can I go deploy? And then after you deploy, you're getting feedback on, well, maybe has anything changed? So there's the desire to use these metrics in both of those scenarios. So a little bit of terminology before I dive into our methods. For this data set, we're going to call it labeled if it's the images plus the ground truth. So we've got the example here of the image plus no plane. Unlabeled is just the image itself, and the metadata is data related to the images. So when you have UAV collection of data, for example, you might have things like the altitude that it's collected at, with some kind of pixel density, ground sample distance. You might have the airspeed of that UAV. You might have the type of sensor that it was using. Unfortunately, we had none of that in this planes data set. So we, to illustrate the concept, kind of derived our own metadata. And we're looking at things that reflect both the location and the image quality itself. So luminance, hue. We also look at RGB color schemes as our metadata categories. And again, I think I defined that we're going to use Southern California as our source data set. Like this is where we did all of our training. And the target data set is the Northern California area where we're moving to. And really the goal here is to understand, is there a difference probabilistically between the source and the target? And how can we use that in the development of all of those questions I posed earlier? So we'll start by defining an operating envelope. So basically, an operating envelope in our definition is a set of all systems to which we can generalize, and we're thinking systems and systems engineering construct here. So this could be the system. If it's just this algorithm is going to be reading images off a computer, that's the system. It's actually the algorithm deployed in a UAV going to collect new information. That's the system. And basically, we're looking at being able to define what's inside that envelope in a quantifiable and also explainable way, and predict what might be outside the envelope is kind of step one to know that we might have a problem. And because we started this in a transfer learning framework, we came up with the concept of transfer distance. But we don't mean it just strictly in a transfer learning construct. It could be you just want to compare between two environments and say how similar are they? Or, as I'll get to in a little bit, you have vendors that are potentially training on test or training on training data, and you have some kind of validation data set for them, and then you want to say that a test data set that you're going to test them on is similar to that validation set, or it's different, but those kinds of questions as well. And so we're defining transfer distance as a bound. So you have the target error and the source error, and transfer distance is just that total distance that's a difference between them, and C is a constant to make all the math work out. And so this is, kind of pictorially, as well as what we are doing for transfer, kind of the concept of transfer distance. And we want to highlight that we're thinking about this in terms of a theoretical framework, but I'm about to dive into, okay, how do we actually estimate this thing? And that's where I think there's a lot of, we've picked our method, and we're exploring all sorts of variations on our method, but we think this holds regardless, because we're basing it in theory to put those bounds on transfer distance. So how do we estimate transfer distance? So we have all of our images that are in data set 1, Southern California, and we know where we want to go in our new data sets. So that's data set 2, Northern California. What we're doing is we're sampling from our source data sets. We're using an autoencoder, and this is, again, here I'm going to get into, here's all the different choices we made. Again, coming back to, we could have used a GAN, but we used, for our first attempt, a variational autoencoder. We get it into compressed latent space, and then we do PCA. in latent space. We extract the first two principal components, and using Gaussian mixture models, we calculate the difference between the density in those principal component distributions. And that's how we're doing transfer distance calculations. So just to show that on our data sets here, here are the two, and we're doing k-fold splits which is how you're getting a distribution of the southern source images here. And so here you can see the southern source images, the first two components of the PCA, once we've done the latent space representation, and the northern target images, the first two principal components. And the corresponding Gaussian mixture models, KL divergence between the two models is here. And so nothing very exciting here, right? We have got confidence intervals that are overlapping. They don't look substantively different. Although hopefully, as we've expanded this to more data sets, we have seen ones that look substantively different and are statistically different just in their latent space representation. But when we add a layer of information, so here when we add labels to it, whether there's planes or no planes, and look at these calculations again, you can see something interesting going on. And so here I've got in the boxes, those are my two misclassification boxes. Whereas in the non-boxes, I've got, those are all correct classifications. So you see an interaction effect between northern and southern, whether or not you're classifying in terms of the rate of misclassification. So we can say that transfer distance is correlated with that misclassification rate. And in the pictures up here, you can now see, okay, well, maybe, from a human interpretable standpoint, that yes, there's maybe something different going on, and that misclassified planes in the northern set have a different center of mass than they do over here in the southern, than the correctly classified planes in the northern set. So I, got all excited about the fact that we had labeled data, and this is really illustrative of Simpson's paradox. So when you don't have that extra piece of information, you're going to say, well, these two things are the same. But you add that extra piece of information, and all of a sudden you're seeing something that's helping you dive a little bit deeper into what's going on. But this is, okay, so I've showed you that a bunch of images based on whether they have a plane or not are different in latent space. What do I do about that, and how does that help me in defining an operating envelope? Well, first of all, what are the strengths of that? So we've defined a metric that's theory-based, it's classifier agnostic, doesn't matter whether they were, whatever, you could have 10 different vendors delivering algorithms to classify planes. None of that factors into this because we picked, a variational autoencoder to directly interpret the images. And it could be label-free. So you could get away with understanding the differences in these spaces without labels. But this isn't human interpretable. So it doesn't get to that explainable dimension that we really want. And I don't know what to do about it. Do I go collect just a bunch more pictures and run them through my VAEs and say, oh, well, these are the next best ones to add? It's not a clear decision-making tool. So we're coupling this ability to understand differences in latent space with this multidimensional kind of envelope construct. So here is a sample of the data set. So you can see northern versus southern. And then on the end, we have our label of plane or no plane. There's no planes in this little cup. And what we've done is extracted metadata based on RGB, red, green, blue, and then hue, illuminance, I forget what B is. And we also looked at their variances, ended up just sticking with the means. But we were trying to come up with some construct that was explainable, that would tell us what is going on different in these images. Ideally, if you have data that's being collected, again, to the UAV platform concept, where you're getting information about the collection itself, what type of sensor it is, what the pixel density is, what altitude the platform was at, what airspeed. All of those things are things that could, in a computer vision, tell you about how likely an algorithm is to do well in those space. And this is kind of an area of research for us, is what metadata is the most meaningful metadata, But once we have metadata that we think is meaningful, we're using it to really define the operating envelope. And so here on the bottom part of the screen, I'm showing how we might use the concept of metadata to understand where my environments overlap. So these P, T, S, R, those we've been using source and target, but P and R, those could all just be different environments. So if we can understand in this space how those environments overlap, we might be able to ensemble or orchestrate our models in a meaningful and informed way. So combinatorial interactions in metadata. So we're going to use a construct actually from software testing, combinatorial interaction testing. And in software testing, it's been used to look at, okay, well, I've got all these code paths, or, these are my on-off settings. How many of them do I cover? We're going to use it to say how much of our metadata or combinatorial space do we cover? And we like this because, first of all, getting back to what decisions do I make, we think this informs decision making in terms of we could use it to guide that transfer computation, select models based on their metadata characteristics. And I'll show in a little bit how we use it to target a retraining strategy. And it's explainable at 3 different levels of complexity. So you can say, okay, this was in the data set or it wasn't, number of interactions present or absent. We can also describe which interactions, so not just there were, this percent were in or out, but you can say, oh, well, red with a plane never saw high values. So not just whether it was there or not, but which. And then also the distribution. And this is critical, I think, in machine learning constructs, because the concept of how much data is enough to train my model, and coming from a classic statistics background, we know if we have a lot of data in one place and very little data in another, that's a high influence point. You can end up with all sorts of biases in your model. And so how do we take those concepts that we know from classic modeling and layer them into machine learning? We're proposing combinatorial coverage and metadata to look at that. So how we actually do that is we look at up to 2-way interactions. So on this slide, I showed a bunch of means, 1, 2, 3, 4, 5, plus a class. So that could be 6 combinations, or sorry, 6 plus 1. And we are looking at how do I choose a subset of those. So if I have 6, I can choose 2, I can choose 3 combinations to describe my space all the way up to 6. And so we'll compute K, the number of metadata character variables that we want to choose T across all of these, and we then compare data. First of all, we can calculate with respect to the universe how much is covered. And that's an existing metric that's been out there in software testing for a while, combinatorial coverage metric, CCM. And it gives you basically a description of the space, how much of that input space is covered. And then, so here's that for our planes data. We're still working on our graphics. These are, it's hard because, so what this is just all possible. There are 72 possible combinations based on the metadata categories that we're looking at here. And so it's either covered or it's not covered. And this is just a visual representation of what's not covered. The banding is actually kind of purposeful. The way we've stacked those, you can see all these class 1 things that are not covered. That's the band you got here. Class 1 across these different combinations. So this is all 2-way in the southern and 2-way in the northern. And it's something I forgot to highlight earlier is that the southern data set is twice as big as the northern data set. Yet when you look at its coverage with respect to these kind of coloring metadata with and without planes, you have more coverage of the different kind of backgrounds in the northern data set, which is why I foreshadowed with like the little desert and the forest. We're seeing more diversity essentially in the backgrounds in the northern data set. And so that is the first thing that you can do with these types of metrics. But when we put the problem in the context of a transfer learning problem or a comparing test sets to validation sets, we might also want to look at set difference combinatorial coverage, which is exactly what it is. So this is a new metric that we derived. We recently published a paper with NIST on it as they're looking at different ways of explaining or developing explainable AI. And basically what set difference combinatorial coverage does is tells you what's in target that's not in source, or you can flip that, what's in source, not in target. And so if you're looking for a representative data set, this image 2 here might be what you're driving towards. If you're looking for something that is completely different, image 5 down here might be what you're looking for. So I want to take this back to our test and evaluation process. And so to me, test and evaluation at its heart is really just about providing sufficient information to support decision making. And so in machine learning, some of the decisions that we might want to make are, is the training set representative of the population for the deployed environment? Some programs, vendors are giving validation sets and told that the test set is representative of that validation set. So can we validate that? Can we say in kind of higher dimensional space, not just simple statistics, that these are representative? Or as we're looking towards more robust concepts in machine learning and AI, can we say that we're testing an algorithm on something that it's never seen before? Novel, or exploiting an unseen context. And so we're using these same methods, not just to assess the difference between two test sets, but also to build test sets that either match some kind of the training or validation set as closely as possible, or exploit unseen contexts. And so here's a picture of what that might look like when you're looking at a validation versus test comparison. And I'll just advance it so if you want to say something matches, you would want to drive your set difference combinatorial coverage metric to 0 in both directions. This is a directional metric, so you can look at things that are in validation and not in tests, or you can flip that and look at things in tests, not in validation. When picking test sets, if you want them to be representative, you drive both of those to 0. And then if you want something that's hard, you're going to drive towards complete separation. Ooh, too many builds, sorry. And so when we look at set difference combinatorial coverage in the plains data set, this really gets towards more of the explainability of what's going on, and it correlates with our transfer distance metrics as well. And so you can see here, if you look at things that are in the southern but not in the northern, there's only 1 out of 60 2A combinations. Whereas if you look at things in the northern data set that are not in the southern, there's 8, which is 12% of your data. And so now we can say, okay, well, these might be a really interesting 8 images, or, you know, there's probably more 8 than 8 images, but go find images that meet this property and let's see what we can do with them. And so the last piece that I want to hit on is kind of closing that loop on what can I do about it. So here's where we're using a transfer learning, and we're doing it in kind of a phased approach where we're saying, okay, we've got our Southern California data and we want to predict in Northern. What's the first thing that we can do when we see that there's a problem? Well, we can characterize that Northern data set, pick out images, and do transfer learning at different layers of our model. And then the third step is we're using a fine-tuning process to further allow us, if we only have limited data in the Northern set, to adding additional features into our model to fine-tune to really optimize on those features. How do we select what parts of the Northern do we compute? Well, we have our source and our target, our Southern and our Northern. What we're actually doing is based on the set difference combinatorial coverage, we're saying, okay, give me all those images that were in the Northern that aren't in the Southern. We'll take a representative of them, and then we'll add them into our training data set. And then of course, to be, you know, not double counting data or testing on what you use to train, we'll remove those from our prediction data set. But since we've taken a sample across them, we still have some that are representative. And so now we have our new data sets, our original Southern California plus a targeted set from Northern California. And then we test on what we were testing on, minus the ones that we added to the Southern data set. And so we've seen some great results in this that not in this data set, and actually we just did it on the MNEST data set, and I was telling David beforehand I wanted to add like 12 more slides to this presentation because we're seeing, when we first presented this, we were like, well, yeah, you know, it's one data set, a little contrived, but here's what we saw. And so you can see here, this is just a callback to our original transfer learning problem. This table on the bottom, a little bit going on, but what the LC is label centric and the NLC is non-label centric. So this is whether or not we're forcing planes equals 1, planes equals 0 as part of our metadata or not. And then you can see if here's just the number of images. So if we pick out targeted data, so that's data that's informed by our set difference combinatorial coverage. Here are our gains in performance. And this baseline here is, that's single shot learning. So no targeted data. But of course, you have to control for the fact that you did add data to your training set. So any data that you add is probably going to lead to improvements. So we want to control for that. And so what we did to control for that is we picked out random data sets. And so here is a plot of the mean for target. If we did the targeted is in blue, mean for the random is in red. And then this is max and mins, which seemed like the best way to present that. And then this black bar is just if we did nothing. And so yes, if you add data, it gets better. That's what the red line says. But when we add the targeted, it gets better based on, and we see that kind of increasing gain as we add more and more images. So that's kind of one of the, so what can I do with it? So in terms of future work, where we're going with this is kind of the roadmap that's in a lot of my head, hopefully most of the team's head, is we have all of this information over here on our source data set. So this is meant to represent the images itself. Our machine learning model is the brain, and the little squared like data sheet thing is our metadata descriptors of that. And so from that, what we've done so far is we've developed these transfer distance metrics. We've developed combinatorial coverage. Something I glossed over completely is, well, what is the right metadata versus and how do you bin that data for combinatorial coverage? So we've looked at optimization routines around those. And some of the most recent work that hot off the presses this past week, we've actually used latent space representations into combinatorial coverage to start to define that operating envelope. One of the things we really like about all of this is that we think it's documentable in model cards. So it's not just, when I'm defining where's my algorithm trained, you can say it's trained on this, it's got this information. This is, if your transfer distance moves outside of this realm, you might be worried. And that allows all sorts of decision-making processes. So that's on the defining the operational envelope, the middle sector here. And then on the right-hand side, there's the what do I do about it? And so we're exploring different options in targeted retraining and the fine-tuning aspects of that, and using all of this information in terms of the models at hand, our combinatorial coverage and transfer distance, to improve the fine-tuning process. So I'll stop by bringing it back to AI assurance because I went a little deep in kind of some of the technical work that we're doing, but I'll hit a few points in terms of why did I cover operating envelopes in such depth. So the constructs that we're thinking about, explainable, I'll start with. If you can define what improves algorithm performance using these metadata characteristics and transfer distance as an early indicator of that, you're moving towards that explainable AI. Again, with fair and unbiased across what dimensions? So if I had a more interesting problem than planes or no planes, maybe I had men, women, and child characterizations, and we wanted to make sure that we weren't systematically predicting women over men or things along those lines. Now that in my metadata categories, I can use this to make sure that I'm getting fair and unbiased and do targeted retuning to address those fair and unbiased concerns. Unreliable and verifiable. When you think about where my algorithms are going to work, if I can say, yep, it's going to work here, I can predict in advance that it's going to work here because I know these are the characteristics of my data. We're getting at that. And so those are the key overlaps, I think, in the operating envelopes to these kind of constructs that we're all, contemplating in AI assurance. So I think we need more and more mechanisms to explore. So with that, I will stop and open it up for questions as I try and go back to the Zoom and find the Q&A tab. Zoom hates me.
David, I have a question for Laura. Okay.
Absolutely, go ask it.
Go ahead.
Great. Laura, thanks. I really enjoyed your talk, and I think that it's, I appreciated the intuitive aspects of it. And I'm wondering if somehow in the coverage approach you take, if this could lead to some kind of a meaningful working metric for confidence for an autonomous system. For example, I'll use the context of a medical diagnosis system. It's presented with some symptoms, and it tells the user, I have some possibilities, but this subspace that I'm waiting in is relatively sparse, so I don't have high confidence, or I have there's some metric of confidence that actually means something. What are your thoughts on that?
Yeah, I think very much so. I'm laughing a little because I'm a statistician, so I have like fear of the word confidence that has been instilled in me for so long. Because everyone wants to say I have confidence. But yes, I think that if you had I think of it as prediction accuracy. And what's the probability for kind of a baby construct that I can see as a future under these conditions? I have this probability that in terms of getting more human description where I can expect my
Okay. Sorry, I'm audio problems. Oh, maybe it's not just me.
Is it, did I?
Yeah, now it's better.
Okay, I missed a good chunk of what
If
you
you could
just
repeat.
said. Sorry.
Yeah.
So the short, I think, version of it is that I have fear of the word confidence because I'm a well-trained statistician. But yes, I think that these could be very informative in developing probability, if you will, kind of credible intervals from a Bayesian perspective to say that probability under these conditions that I see this performance is X. You could completely do that once you have the coverage construct and being able to do predictive prediction intervals with confidence levels is something we could do, right now. Here's my prediction score. What's the, confidence that I see something in that bound going forward?
Yep.
Condition X, Y, and Z.
And even explainability of the confidence based on sparseness or something like that, which would be even better.
Yeah.
Thank you.
I have a question, Laura. So in doing the transfer learning and moving from one domain to another, I think you're looking at data that you believe is true. But when you're dealing with adversarial conditions, what does that do to the measure of distance and I don't want to bring up the confidence issue again, but how do you address moving from one domain to another under adversarial conditions?
Yeah, so I don't think this is not a panacea for all sorts of things like that. What I do think transfer distance could do, and combinatorial coverage, if you've defined it in kind of the right metadata, is provide early indicators that you're operating in an adversarial environment. So we put this on our UAV and we're up patrolling, and all of a sudden, people are putting glint refractors everywhere out there in the field. That's going to register in your transfer distance metric. Transfer distance isn't going to tell you what's going on, but it's going to tell you that something about the space that you're looking at has changed. And so I see transfer distance as potentially an early indicator, but as we saw in the plains data set, it's not a very sensitive early indicator. To see differences in latent space, or at least on some of the work that we've seen so far, you need a pretty good change. And so I think there's some work in how do you, or at least our variational encoder version of transfer distance is not very sensitive. So developing more sensitive indicators of distance in combination with, if we're collecting information in real time about environments on the ground, that could provide a more sensitive indicator. But I see this as kind of an early indicator that, okay, something has changed. It could be due to adversarial nature. It could be changing in the environment. It could be, I don't know, my sensor's going bad, all sorts of things. But it would provide that early indicator. And one of the things that I think is an area for research is right now transfer distance is computationally intensive, as we've defined it. So is there a less computational, could be at the edge version of transfer distance that's giving you that real-time feedback? That coupled with actual, tracking of your performance, multivariate methods are always more sensitive than univariate methods. So if you're tracking performance and you're tracking transfer distance and you're tracking your metadata, if they're coming in kind of in real time, as our UAV example gives, the three of those could be, a powerful tool in detecting adversarial actions. All right, so there's a question in the chat. How scalable do you think these methods are for more complex ML systems and even more complex environments? For example, do you expect these methods to be useful for the recent crop of extremely large deep learning networks? What about for drones or self-driving cars deployed in very complex urban environments? So yes, in that, well, so first of all, neither transfer distance nor combinatorial coverage is dependent on the complexity of the ML model. And that's sort of foundational to a lot of the research that I do, in that I'm assuming that no one's ever going to give me the model. It's the vendor's secret sauce. They're not going to sell it out for any reason. And so both of these were purposefully designed to be model agnostic. And so therefore they are scalable to, really the driving force for scalability is how much data do you have? And we've used combinatorial coverage in environments with millions and millions and millions of rows of data, and there it's just a compute to to time ratio. What is hard about how scalable are these to complex environments is understanding from a machine learning background what features matter. So in full motion video, computer vision, we've gotten kind of general awareness in the community that things like contrast matter, how good of a view you have, if you will, of the image. Background matters, when you're using CNNs, it's sliding along looking for edges, all those things matter. And so we have some rationale for the selection of our metadata categories because they're actually getting at what drives the algorithm performance. When you get into models that you really don't know how they're working, or they're in environments that are complex, how you define what matters and going through that process needs to be, I think, learned itself. And that's where it gets, I don't exactly know. So, okay, so now we want to do this in natural language processing. What does that look like? What features matter for machine learning features or metadata? What am I actually looking at in latent space? Am I pick a different decomposition, obviously, for latent space from a variational autoencoder. Maybe I'm using, some kind of NLP model, Centivec, Doctivec, whatever. And you're decomposing it that way. But is that useful? I don't know. We haven't tackled that yet. So I think that's the harder part about the scalability and extensibility of these methods. We started in a domain where we know what we're doing, and kind of how they extrapolate is an open question. So the next question, can you say something more about theme 5 risk-based test approach? Thanks, Richard, great question. So a lot of the risk going in here is thinking about how do I quantify my envelope, and then what risks do I have in performance going forward. But what kind of more holistically diving down into a risk-based test approach, we need the ability when we go through test and evaluation to say, this is how much data I have, this is how well I understand what's going on, and iteratively add onto that. And so that comes back to the, I think the question that we had earlier on confidence from Tony, in terms of at each point in this process, I need to quantify my risk in terms of my algorithm's performance and my algorithm's performance across different conditions, and iteratively add on to that. So that's very high level to say things like, okay, well, so once we quantify it across all these things, I have a new environment, that's a new area of risk. How can I use things like optimal learning to fill in that gap? Or how do I know how much data I need? And turning that into a risk-based solution. And so I'm thinking of that right now, just to kind of go back to that piece on prediction intervals, but it's basically for a machine learning algorithm, if I can predict what it's going to do before I see what it's going to do, that is buying down my risk. And that's the goal for me, is being able to predict what's going to happen before I see it in a new environment. And so that's the construct that we're operating under, kind of for a framework for risk-based testing, is that, how frequently can I do that versus when I cannot do that at the highest level? What's that probability?
May I ask a question? Can you hear me?
Yes, I can hear you.
Yeah, hi, I work in computer vision, Rama Chalapa, and since 2010, we have been looking at domain adaptation because data shift is a big issue for us when you collect data from two different sensors or two different environments and so on. So transfer learning, we kind of view as a cousin to domain adaptation. There are these definitions in terms of marginals and so forth. Anyway, I was just thinking of MMD from Mike Jordan's group, as one way of measuring the domain shift. And we have done Wasserstein distance, especially when we use mixture of Gaussians or both source and data. I sent you some of these papers, but anyway, I thought I'll just bring to your attention this domain adaptation has become one of the hot areas in computer vision, because to me, every pattern recognition problem is a domain adaptation problem. There's no way you're going to have a test data like the training data anyway. So anyway, I thought I'll just mention these things. Thank you. I enjoyed your talk.
Thank you. All right.
Okay. Thank you so much, Laura. It was an amazing talk. I think everybody enjoyed it, and you provided lots of deep insight into the problem. So on behalf of the Institute for Assured Autonomy and the Whiting School of Engineering, thank you very much for your presentation.
Thank you for the invite. It was nice to see you all.
Thanks, Laura.
Again, Laura.
Thanks, Laura.